Welcome to the Neuromodulation Podcast, presented to you by the International Neuromodulation Society. Dive into the forefront of today's emerging neuromodulation techniques, insights, and ethical and clinical applications. Subscribe now to join the multidisciplinary collaboration of medical care providers, scientists, and engineers who are part of the global conversation that's shaping the future of healthcare. Welcome to the Biostatistics articles live reading series, presented by the International Neuromodulation Society and developed in collaboration with the Newcastle Cognition Lab at the University of Newcastle. I'm your host, Mandy Soleil, and it's a pleasure to have you here. We're pleased to offer this ongoing series of short articles explaining how to critically apprise clinically relevant literature to evaluate evidence and inform practice. The entire series of articles is available on our website at www.neuromodulation.com/biostatistics-articles, and a direct link to this article is available in the episode show notes. We've translated each article to a live episode on the Neuromodulation podcast to bring versatility and ease to your statistics learning journey. Each primer features a single topic and an example within the context of clinical neuromodulation research and practice. Upon reading and/or listening to these articles, learners will be able to understand statistical methods, their interpretation and their limitations, identify cognitive biases to avoid inadvertently misinterpreting evidence, and interpret data for a deeper understanding of clinical research to inform clinical practice. And now, I present to you Professor Konstantin Slavin, head of the Stereotactic and Functional Neurosurgery section at the University of Illinois Chicago, or UIC, and president-elect of the INS. His term as president begins September 1st, 2024. Thank you for tuning in.
The podcast today is a review of the biostatistical publications that are written specifically for the International Neuromodulation Society. We have a series of them on our website, and my goal today is to read one aloud so people can use it for enhancement of their biostatistical knowledge. So the first in a series of biostatistic articles written for INS is a one on how to interpret a Bayes factor. It is written by Quentin Gronau, Garston Liang, and Alexander Thorpe. The summary of the paper deals with the Bayes factor, which, when it's F10, is a ratio that quantifies evidence in favor of an effect represented by 1 in the subscript versus no effect represented by 0 in the subscript. BF10 more than 1 indicates evidence in favor of an effect. BF10 more than 0 and less than 1 indicates evidence in favor of no effect. BF10 equals 1 indicates that the data are ambiguous. Part 1. Bayes factor replaces p-values. For many years, null hypothesis significance testing using p-values has been the ubiquitous approach for testing hypotheses such as whether or not a new chronic pain management therapy outperforms an existing therapy. However, this approach has many flaws, which often results in p-values being misused and misinterpreted. Bayesian inference provides an alternative approach which addresses many of these flaws, which can in principle be applied to in any situation where one would report a p-value. When testing hypotheses using Bayesian inference, p-values are replaced by Bayes factors. Bayes factors offer a number of practical benefits compared to p-values, such as enabling the quantification of evidence in favor of the null hypothesis, for example, when two therapy forms being equally effective, and allowing sequential monitoring of evidence as observations arrive. However, to draw valid conclusions, it is crucial that they are interpreted correctly. Part 2. Bayes factor interpretation. Bayes factor allows researchers and practitioners to assess the evidence that the data provide for an effect being present or absent. Suppose the null hypothesis, which is H0, corresponds to a new therapy being equally effective as an existing one. In contrast, the alternative hypothesis, which is marked as H1, corresponds to the new therapy outperforming the existing one. The Bayes factor compares how well each hypothesis has predicted the observed data. a base factor, for instance, BF10 equals 11, indicates that the observed data are 11 times more likely under hypothesis 1, which states that the new therapy is more effective, than under hypothesis 0, which states that both therapy are equally effective. In general, values of base factor 10 larger than 1 indicate evidence in favor of hypothesis 1, meaning that effect is present. Values between 0 and 1 indicate evidence in favor of hypothesis 0, meaning that there is no effect. Base factor cannot be negatives. When interpreting a base factor, it is important to pay attention to the order of the subscripts. Specifically, 1 corresponds to hypothesis 1 and 0 corresponds to hypothesis 0. Consequently, BF base factor 10 expresses evidence of hypothesis 1 over hypothesis 0. However, when base factor 10 is smaller than 1, for instance, base factor 10 equals to 0.5, and thus indicates evidence for hypothesis 0, it is common practice to re-express the base factor in favor of hypothesis 0 as follows. Base factor of 0, 1 equals 1 divided by base factor 1, 0, meaning that 1 divided by 0.5 equals 2. This does not change the evidence, but it's simply a different way of presenting it. In contrast to p-values, base factors cannot be significant, as they are a continuous measure of evidence. However, to aid interpretation, labels for different degrees of evidence have been proposed, and it's illustrated in the figure 1, which I'll stop by in a second. Furthermore, an intuition for the strength of evidence a base factor provides can be obtained by using the urn analogy and the spinner analogy. So let's look at the figure 1. Figure 1 illustrates 3 different base factors. Base factor of 1 to 0 equals 11, base factors of 1 to 0 equals 1, and base factor of 0 to 1 equals 2. So in the first one, where base factor 1 to 0 equals 11, there are 12 balls within the urn, and 11 of them are red and 1 is black, meaning that 11 out of 12 chance that the red ball will be pulled rather than the gray one. When base factor 10 equals 1, there are only 2 spheres in the urn, and one of them is red and one is gray, meaning that there's equal chance of them being pulled. When base factor 0 to 1 equals 2, there are 2 gray ones and 1 red, meaning that there's 2 chances out of 3 that the gray hypothesis, which is hypothesis 0, will be the correct one. So in a degree of grading, base factor between 1 and 3 suggests that evidence is anecdotal. 3 to 10 suggests that evidence is moderate. 10 to 30 suggests that evidence is strong. 30 to 100 suggests that evidence is very strong. And more than 100 suggests that evidence is extreme. So in explanation for the figure, there's a specific mention that the base factor indicates the probability of the or likelihood of the hypothesis, which would be with factor equals 11. It would indicate that the data are 11 times more likely under the alternative hypothesis, meaning that effect is present, represented by number 1 in the subscript, rather than null hypothesis, meaning that there is no effect, represented by 0 in a subscript. This is considered strong evidence for an effect. For base factor of 2, 0 to 1, factor of 2 indicates that the data are 2 times more likely under null hypothesis, which is 0, rather than alternative hypothesis, which is 1. This is considered anecdotal evidence for no effect. The urn analogy works as follows. Suppose the base factor is base factor 10 equals 11. This is analogous to putting 11 red balls corresponding to hypothesis 1 and 1 gray ball corresponding to hypothesis 0 into an urn. Suppose you draw a ball at random and end up drawing a single gray ball, which is obviously possible. Your level of surprise provides an intuition for the strength of evidence. In this case, you might be quite surprised, indicating that a base factor of 11 provides strong evidence. In contrast, suppose base factor 1 to 0 equals 0.5. Since the base factor is smaller than 1, it is easier to express it in favor of the null hypothesis, meaning that base factor 0 to 1, which is 1 divided by 0.5, equals 2. This is analogous to placing 2 gray balls corresponding to hypothesis 0 and 1 red ball corresponding to hypothesis 1 into an urn. And if you end up drawing the single red ball, you may not be very surprised, indicating that this base factor does not provide much evidence. The spinner analogy works in a similar manner and is relevant because it is used in the output of statistical software such as JASP, available at the website jasp-stats.org. Instead of placing balls into an urn, one creates a pie chart where the ratio of red and gray area is in line with observed Bayes factor. For instance, for Bayes factor 1 to 0 equals 11, one creates a pie chart where the ratio of the area colored in red versus gray is 11 to 1. Next, imagine attaching a spinner to this pie chart and spinning it. Suppose a spinner ends up in a smaller, in this case, gray area. Your level of surprise provides you with an intuition for the strength of evidence. Similarly, for Bayes factor 0 to 1 equals 2, one constructs a pie chart where the ratio of the area colored in gray versus red is 2 to 1, and imagine the spinner ends up again in a smaller, in this case, red area. In sum, Bayes factors are easily interpretable, and in contrast to p-values, enable one to assess the evidence in favor of an effect being present or absent. To highlight this, suppose a t-test comparing two therapy yields p-value of 0.03. This p-value is significant because it's lower than 0.05. However, only Bayes factor can tell how much evidence there really is. Suppose the number of participants being exposed to each therapy was 20. In this case, Bayes factor 1 to 0 equals 2.18, indicating only anecdotal evidence in favor of an effect. Alternatively, suppose the number of participants being exposed to each therapy was 5,000. In this case, Bayes factor 0 to 1, which is equal to 1 divided by Bayes factor of 1 to 0, is 4.22. Therefore, although the p-value is significant, the Bayes factor indicates that there is in fact moderate evidence in favor of no effect. Part 3. Common misconceptions. When interpreting Bayes factor, there are a number of common misconceptions that one should be aware of. Misconception 1. A Bayes factor of about 1 indicates evidence for the null hypothesis, meaning no effect. A Bayes factor of about 1 indicates that the data are about equally likely under hypothesis 1 and hypothesis 0. Their evidence is ambiguous. In contrast, if Bayes factor is smaller than 1, or equivalently, Bayes factor of 0 to 1 is larger than 1, this indicates evidence for the null hypothesis. One strength of Bayes factor is that this way, they can disentangle evidence of absence, meaning evidence in favor of hypothesis 0, from absence of evidence, meaning ambiguous evidence where the Bayes factor is about 1. This is not possible with p-values. Misconception number 2. Treating Bayes factors larger versus smaller than 10 is as significant versus non-significant. While it is true that Bayes factor larger than 10 are considered strong evidence, a Bayes factor of 1 to 0 equals 9.9 does not provide fundamentally different evidence from Bayes factor 1 to 0 of 10.1. The Bayes factor is a continuous measure of evidence, in contrast to dichotomous significant versus non-significant p-values. The evidence labels merely serve as interpretation aid. Misconception 3. Interpreting Bayes factors close to 1 as strong evidence. While it might sound at first glance impressive that the data are, for instance, 2 times more likely under hypothesis 1 than under hypothesis 0, considering analogies such as urn or spinner and the evidence labels highlight that such Bayes factors do not provide much evidence. Part 4 has further reading. There are few resources that provide greater introduction to Bayesian inference in general and Bayesian hypothesis testing using Bayes factors in particular. One is a paper by Wagenmakers from 2018 published in Psychonomic Bulletin and Review. The second one is by Etz and colleagues from 2018 published in Psychonomic Bulletin and Review. And the third one is by Wagenmakers and colleagues, also written in 2018, specifically dealing with Bayesian inference for psychology, which is the second part of the first reference, and it's published in Psychonomic Bulletin and Review, volume 25. Thank you.